Another thing we can do to, I guess, manipulate K, but just to use it in a couple different ways, is to use equilibrium constant expressions both as something that represents ratios of concentrations and ratios of partial pressures. And while the concept is the same, it's really just representing the amount of products versus the amount of reactants. Because the units are fundamentally different between molarity and atmospheres or torr or PSI, but because those are different, we actually see a difference in the value of the K. And we always are going to use atmospheres for calculating K, and we'll always use molarity for calculating K if we're using concentrations. And so we've actually developed a way of converting between equilibrium constant based on concentration versus an equilibrium constant based just on partial pressure. Now, concentration, remember, is molarity, moles per liter. That can represent the moles of solute per volume of solution, but it can also be that moles of a gas in a volume of a container within a gas mixture. And so that partial pressure and concentration are really the same thing. It's just, again, we've got a unit difference that needs to be dealt with. So we can express it either way. And here it is written out for Kp, which we will designate with a subscript P if we're using pressures, and we'll use a subscript C if we're using concentrations. And we typically, maybe it's just me, but I feel like I've used concentrations more than I've used pressures, but they're both the same. So instead of doing the concentration of C, you'll do the partial pressure of C in this expression. And again, it's important that this is in atmospheres. So we can create an expression that relates the equilibrium constant for pressures to the equilibrium constant for concentrations. It's listed right here. That Kp value for when we're using partial pressures will be equal to the equilibrium constant when we use concentrations times RT all to the power of the change in N. So what are all those things? So R is our universal gas law constant. Since we're using atmospheres, we're going to very specifically use the 0.0821 liters times atmospheres divided by moles Kelvin. That means our temperature is also going to be in units of Kelvin. This delta N, this is the difference in the number of moles between the reactants and the products. And so it's going to be the number of moles of the products minus the number of moles of the reactants. And that really is just the sum of the coefficients. And we see that when there's no difference between those number of moles, when that delta N is 0, we actually have the K equal when it's a pressure K to a concentration K. So when we're thinking about these reactants, we can say, and product moles, if I had something like, let's do like, here, let's just do it as this. We'll use variables. So my delta N here is going to be my C plus D. So the sum of the coefficients for my products minus the sum of the coefficients for my reactants. Let's look at an example. So we're looking at the NO2 combining and forming N2O4. We were previously looking at the reverse of this, where we were looking at the decomposition of N2O4. So our Kp value is equal to 0.480. This is at 25 degrees Celsius. And we want to know what is the Kc value that we have here at the same temperature. So we're going to use our equation that Kp equals Kc divided by RT to the change in N, and rearrange it so that way we have, we'll be calculating our Kc value right here. So we can input our Kp value. Now our R and our T, our R is a constant and T is our 25 degrees Celsius converted into Kelvin. And then here is our delta N. So our delta N equals -1. And so what that's coming from is our coefficients are 1 and 2, right? So remember, it's going to be products minus reactants. So I have a sum of coefficients of 1 for my products minus the coefficients for my reactants summed together, and there's only 1. So it's minus 2. That equals -1. So when I calculate all of this, the K value that I calculate is 11.7, which is kind of extremely different.